Oh, yes.
Yeah, I think it's TI-36.
Huh?
I think it's TI-36.
Like I thought. Oh, yeah, this is fast. Be quiet.
Can you show it to me later?
Yeah.
So I can just get to the lesson. Yeah.
No, I apologize.
I think that's what I didn't show you before. Should I show you that after class?
Yeah, show it to me later. Okay. So we're going to be preparing for the calculator portion, guys. Calculator portion for your Unit 6 test. It'll just be 3 free response questions. So let me just kind of show you what it will look like. One will be something related to a derivative graph, like page 3. We'll get through. We'll go through something like that. Another problem will be involving Riemann sums, which we're just doing left-handed rectangles, trapezoids, middle rectangles. You should find this pretty easy. And then the last will be a full particle motion problem involving integrals. So we'll also practice. So really just these 2 problems. We'll just go through them over the course of today and Monday. I'm going to start the next unit on differential equations on Tuesday. But this chapter or this calculator portion test, I'm scheduled for next Thursday. Okay, that way we have 2 full days in class, and you guys can continue to practice on your own. I can also have some help sessions Tuesday and Wednesday of next week, so that it doesn't feel rushed preparing for this portion of the test. But I can also start the next unit on differential equations starting on Tuesday. Okay. All right, so you guys will need your calculator. I really encourage you guys to get your hands on 83, 84, or one of the graphing calculators. I mean, you can get away with 36, but it is a little cumbersome not being able to see the graph and having to just use your table of values. You can still do it, but it's just more efficient with the graphing calculator. Okay, so hopefully eventually you can buy one or get one. I do have some older graphing calculators that you can kind of use in the meantime, but yeah, on the test you can have both the 36 Pro and graphing calculator if you like. That's fine. Okay, so let's start with number 1 here. Just want to introduce some things to you. A particle moves along the y-axis. So this is a particle motion, but then instead of moving horizontally, it's moving vertically. Given by v of t. V of t is t sine of t squared. In which direction is the particle moving at time t equals 1.5? So I can just plug 1.5 into the what? T value of my velocity, right? And if I get a positive velocity, what does that mean? That means my velocity. That means my object is moving up. Yeah, because it's either moving up or down. Right? It's not left or right. If it was left or right, then positive would mean moving right. If I get a negative velocity, that means it's moving down. Yeah. So we're just simply having to enter this in the calculator. But I want to show you how if we just enter it under y equals, we can just continue calling the function without having to retype it in every time. So under y equals, first off, make sure that you're in radian mode. you're gonna go to mode. I want to try something here. Give me 1 second. I found a TI-84 emulator online. Maybe that's a little easier to see. Let me see if I can get that showing up. Share that screen. Yeah, zoom in on that. Okay, so we're going to go to y equals. First, you can click on mode, right? If you click on mode, you can confirm that you are in radian mode. Okay, and then go to y equals. And instead of t sine t squared, you're going to enter in x sine x squared. So anytime you see a variable in your calculator, always use x. Okay, don't try to match whatever variable that is in the problem. Always use x, otherwise the calculator will complain or give you something that you don't want. So x is this button with all the other variables. So you'll do x sine x squared. Next up, you're going to go to second mode. Second mode will take you back to your home screen. Second mode takes you back to your home screen. Okay, so now that you're back at your home screen, you're going to go to math. I'm sorry, let me try this again. Alpha y equals, you see what is it? Alpha trace, I think. There it is. Alpha trace. If you do alpha trace, you see how you have all these options under y1, y2. Right now, my velocity function is stored under y1. And then do parentheses, and I'm just going to plug in 1.5 into my velocity function. So this is a nice feature because you don't have to type in, if there's multiple x's, you don't have to type in that entry into every variable. The calculator will just do it for you. So, so I can say that my velocity at 1.5 is equal to 1.167, which is greater than 0. Therefore, I can say that my particle is moving up. Okay, part B, find the acceleration of the particle at time t equals 1.5. So acceleration is the what of velocity? Derivative. So basically, I just have to do v prime of 1.5, right? Now, these calculators are not able to find the derivative function, but it can evaluate the derivative at a point. So what you can do is you're going to go to math, see that math 8. And then if you're using a 36 Pro, there's also that button that you can find derivative where you can get that, see that notation there. And then you'll do d over dx. And then you're going to type in your velocity function, but rather than typing in your velocity function, Let's just call that velocity function that is stored under y1. So again, go to alpha trace, select y1, and then we're going to make the calculator evaluate the derivative at x equals 1.5. Hit enter. So gets you your acceleration without having to type in. You can just once you have that velocity function stored, we can just continue to use it over and over again. So b prime 1.5 is negative 2.049. You either round it up or you can truncate. So whatever you do, just get it to 3 decimal places. That's the standard. Okay. So here's my acceleration. Is my velocity increasing or decreasing? Decreasing because my velocity is less than 0, right? Sorry, velocity is decreasing because acceleration is less than 0, sorry. Okay, so within this problem, we're going to kind of see all the calculus features that we're going to need to know on the calculator. So it says, given that y of t is position, and that y of 0 equals 3, find y of 2. So I like to go through this formula because this kind of helps me think in terms of particle motion. So here's the formula. If I'm looking for a location, and so my unknown location or unknown position is equal to my known position plus whatever the displacement is between those 2 points. So if I start off at location 3, and then if I have my displacement, I move another right 4 units, then 3 plus 4 equals 7. So I'm just always going, this is basically just also a rearranging of first theorem, but it is put it in a way where it just feels like a particle motion problem, okay? I'm looking for final position. I have a starting position, and let's figure out how much distance I covered between those 2 points to get to my final position. So if I want to find, I'm going to adapt this equation for my problem here. So if I want to find y of 2, it's equal to y of 0 plus however much I traveled between 0 and 2, my displacement. Right? So the antiderivative of my velocity is going to give me how much change in position I'm going to travel in that distance. So my y of 0 is just 3, so I'll come back to that. Now this is something that we can plug in the calculator. And the calculator is not going to give you an indefinite integral, but it can give you a definite integral. So what you're going to do is you're going to go to math, but math 8 is derivative, math 9 is definite integrals. So do math 9. So you can scroll down to 9, or you can just hit 9 on your button. And you'll see that definite integral notation showing up. So we'll just go from 0 to 2. And again, call your velocity function, which is stored under y1. So do alpha trace, yeah. y1. Make sure you finish off with dx. So we know that between 0 and 2 seconds, this object is going to travel 0.8 units to the up. And then we can have our starting position. So what's y of 0 equal to? 3. So we know that at 3 seconds, this object is going to end up 3.826 units up on the y-axis. Okay, finally, find total distance. This is also a calculator setup. Total distance is just the absolute value. And the reason why we need absolute value is because if this object is backtracking, if the velocity function has parts of it above and below the x-axis, we want to make sure that the below portion counts as a positive distance. So, but we'll make the calc do all the work for us. We just have to do a depth integral from 0 to 2 of the absolute value of velocity. This will give us total distance. Basically, any velocity function where I have above and below, the absolute value will translate all those negative areas into positive areas.
So that does the same thing as the sign line, basically.
Yeah, it does the same thing as having to do the sign line and adjusting. Calculator would do all that in just one step. So let's see if we can practice getting to that feature. So in your calculator, you're going to go to, go to Math 9, type in 0 and 2. Now, if you go to math, hit math, which is on that first column here. Couple buttons down. So math, and then you're going to scroll over to NUM number. You see that ABS there? So that's your absolute value feature. So math num ABS. Hit enter. Your absolute value notation will show up. Make sure your absolute value is only surrounding your velocity. You're not making it surround the entire integral. It's just surrounding your velocity. So now you can call your velocity function. So alpha trace y1. Still the same velocity function we've been working with. And then close it dx. Typically, this takes a little bit longer to calculate, so just have to wait a little bit. There it is. So we know this, so after all the backtracking that this object travels a distance of 1.173 units. Okay, any questions? Anybody have any questions on their calculator? Okay, all right, let's look at number 2. Number 2 is a problem that we can also involve Riemann sum. So let's go to,
So like for the exam, can I just put the answer or do I have to show your work? I don't.
you will not have to show your work. Yeah. Okay, so here's 2. All right, the temperature in degrees Celsius of water in a pond in the differentiable function. So we just know that's a smooth curve all the way through. There's not, we only see a couple of order pairs here, but we know there's nothing. That's the temperature is going to, it's going to fluctuate, but there's not going to be any jumps in this graph. Table above shows the water temperature is recorded every 3 days over a 15-day period. So that means day 0, temperature of the water is 20 degrees. Day 3 is 31 degrees, 28, 24, 22. So it peaks at 31, or we think it peaks at 31, but then it goes down to 21. Okay, use the data to approximate W prime of 12. So W prime of 12, this is asking for the derivative, but we don't have a function to plug in, so derivative, we can think of what this is just approximating a derivative means we can use what? Find a slope, right? Just the rate of change. So if I want to find the slope around 12, I can pick any two order pairs in this region and just find the slope, right? Change in temperature over change in days. So if your target point lands exactly on your order pair, then you have options. They can use either these two order pairs, you can use these two order pairs, or you can even use these two order pairs. But anything that is further away is not accurate enough. So you pick any two order pairs you want, and then just find the slope between those two. Okay, so we'll say W prime of 12 is roughly, I'm going to say approximated because I don't know the exact rate of change. I'm just going to pick the last two here, but if you chose different order pairs, that's fine. So I'll say W of 15 minus W of 12 over 15 minus 12. So change in temperature over the change in time. So roughly on the 12th day, the temperature inside the pond is decreasing on the 12th day at negative 1/3 Celsius per day. Part B, approximate the average temperature over the course using trapezoid approximation. So average temperature, we're going to take advantage of average value theorem. So basically, we're going to approximate the area under all this, accumulate all the temperatures divided by the number of days, and then we're going to get an average temperature across all these temperatures, or at least find an approximation. So 1 over B minus A, so 1 over, well, just 15 days, right? So 1 over B minus A, my A and B value are 15 and 0. Okay, trapezoids. So we got to do trapezoids between 1 and 15. Okay, yeah, so
We do intervals of 5.
intervals of 3.
Oh.
Right, my width is 3.
The width is 5.
Hmm?
The width is 5.
The width is 5.
15 minus 0 over.
Right. Well, but the thing is, we have to use the table that is given to us, right? So, sorry, this is a little bit tedious. On the test, I think on most test questions, you're not going to have as many intervals to deal with. But let's do this. Okay. So the trapezoid approximation or trapezoid area is width over 2 or 1/2 width, height 1 plus height 2. So every width is 3, but on your Riemann-Stone's problem, you're not going to have the same width. Okay, but in this case, the width is all the same. So I'm just going to focus on this portion first. And then after I get that area approximation, I'll divide by 15. So it's going to feel a little tedious because there's so many areas to calculate, but you won't have as many to have to do on the test. Let's go practice with trapezoids since this is the rule that we're less familiar with compared to rectangles.
Does it matter if we go from like right to left?
I like to go from left to right, but it probably doesn't matter. Okay, so let's skip all the calculations here so that you know that this is you're just entering all this into your calculator. All that is going to end up giving you 376.5. The integral is going to be represented as area, so we're approximating this value. So 376.5 divided by 15. We should get something that makes sense, right? We're looking at all these temperature. I mean, our average temperature should land somewhere between 20 and 31 degrees, right? Probably somewhere in between. So if we're getting a number that is, we don't want to say 376 is our average temperature, right? That doesn't make sense. So you're missing something there. You got to divide by 15. So we have all these order pairs, but then part C, it says now a student is going to propose that there is an actual function that can give us more detailed information about how the temperature is changing in that pond at any moment in time, not just every 3 days. So now we can find P prime of 12. We can find a more accurate approximation or a more accurate rate of change. So we can make the calculator do this work for us. We don't have to find the derivative by hand. Let's just make the calculator call that math 8 feature, right? So now I'm going to call this, put this under Y2. You can erase Y1 if you want. Put this under Y2. Type this in again. Any variable that you see, instead use what? X. Yeah, always use X. Don't ever try to use other variables. It was just the calculator will complain or it won't give you what you want. Oh, there is a fractional button in your calculator. If you do alpha y equals, there's that n over d feature there. And that will give you a nice numerator denominator fractional notation, which will allow you to avoid having to create parentheses. It's just it's more similar to your 36 Pro. Okay, so 20 plus 10x e to the negative x over 3. Go back to my home screen so I can do second mode. Now I want to find P prime of 12, so that's math 8. Just type everything in. D over dx. You know that your function is stored under Y2. And then I want to find P prime of 12, so Y prime of 12. So it's a little bit more accurate than what we did here. This one, we got negative 1/3, but here we're getting negative 0.549, which supposedly is more accurate. So this tells us that on the 12th day, the temperature is decreasing by a rate of about 0.5 degrees Celsius per day. Part D, we're going to do average value, but now we're going to do average value with a function that we can plug in instead of doing approximation using geometric shapes. So same formula, we just now have a function to plug in. So I'll do that 1/15, math 9, depth integral from 0 to 15. Alpha trace, call your function. It should resemble my approximation, but it's supposedly more accurate now. Okay, so I like this problem. I like these two problems because we got a chance to see all the majority features that we need to know on the test and as well as on the exam. The only thing we haven't quite gone over is the graphing, but we're not going to quite have to deal with the graphing just yet. We will talk about those graphing features a little bit later. Okay, won't be on this test. Okay, let's go to page 2. Okay, the graph is shown. This graph is called the G function. I'm sorry, the graph of f is shown. This is f of t. But everything that the problem is asking for is in terms of g. So here's the relationship. They tell us g is the antiderivative of f. So let me go ahead and write that down here under A. So if g is the integral of f of t, then g prime must be the what of this function? Good. So we're doing a little bit of second theorem, right? You don't have to show all the second theorem step. I just want to just prove to you that this will just turn into f of t, sorry, f of x, because it's upper bound times lower bound's derivative, right? Also, this also makes sense because right now g is sitting at a level above f. So if I find g prime, then that's going to drag it down to f level. So g prime is just f. So whenever you see this notation, just know that there's a derivative relationship here going on between g and f. Right? So we know that g prime is f. And if I keep going down that line of thinking, then g double prime is just going to be what? Just f prime. So there's that staggered relationship between g and f. Now, what's most important here is that if this is the f, then we can also call this what? G prime. So this is the derivative graph, right? This is the derivative graph of g because of this relationship that they established. Now, if this is the derivative graph, then let's go ahead and label in terms of what this means for the g graph, right? We know that this is not the actual g graph. This is the derivative g graph. So we know that anything above the x-axis will be where my g graph is rising. Below is where my g graph is falling. On the x-axis is where my g graph is experiencing a slope 0. But it's asking for g of 0, g prime of 0, and g double prime of -1. So all we need to do is to rely on the definitions that we've established here. So let's find g of 0 first. So to find g of 0, we just use the g of x function and just do whatever it tells us to do. Now, whenever I read the graph whenever I'm trying to read information from a graph, I prefer left to right. If I don't see left to right, then I like to switch the bounds and adjust. Okay. But if I'm doing a depth integral problem where I'm just going through first theorem, then I don't care if the bounds are out of order. But here, if I'm trying to read the graph, then I like my order of the bounds being the same, being smaller to larger. Is this one okay? This one's fine, right? So I want to look at the region between the graph and the x-axis. Now there are multiple shapes going on, but you want to make sure that you are looking in the region between the graph and the x-axis. Don't try to shade in other parts because those are not part of our diagram. So if you want to shade in lightly the parts that matters, then that way we're not getting thrown off by other shapes that we see. So just lightly shade in between the graph and the x-axis. So when you go back and find the areas, that you're not accidentally looking at areas in other regions, right? You're just going to look at those regions. Okay, so from -3 to 0, I'm looking at this region here, right? -3 to 0. It's all above the x-axis. So if you don't want to use trapezoid area, that's fine, because you can always split up a trapezoid into rectangle and triangle, if that makes it easier. So here I see a triangle on top of a rectangle, so maybe it's just easier to think in terms of adding areas of easier shapes. So what's the area of my rectangle here? 3, length times width. What's the area of my triangle there? Mhm.
1.5.
Yeah, 1.5. So the definite integral from -3 to 0 of f of t is simply just what? 4.5. Okay, so here's the relationship between g and f. We know that g prime of x equals f of x. Let's find g prime of 0. So g prime of 0 is just f of 0. And f of 0 is just the what?
1.
Just the order pair, right? This is my f graph. Before I was looking for area, now I'm just looking for the order pair. F of 0 equals 1. G double prime of -1. So let's see what that relationship is in terms of f. It's f prime of -1. So f prime of -1 is not asking for area, it's not asking for the order pair, it's asking for the what of f, slope. Okay. Now, if I ask you for slope, I'm going to ask it along a nice diagonal line. Okay. It's not the only way I can ask you along the semicircle is if it's like a slope 0. Otherwise, you're not going to know what that is unless you have a formula to plug into. Okay, so -1. It's up here. So if I can find the slope of this line, I have the slope of my f graph at -1. Okay, what's the slope of this line segment? Down 1 over 3, right? So -1/3, right? Okay. Okay, good so far. Part C, find all the values where we attain a relative maximum for the G graph. So this is where we can create our slope sine line, so we can get a visual as to how our graph is moving using these arrows, right? So where are my critical points for my G prime sine line?
-4.
Mm-hmm.
X equals 1
Mm-hmm.
and x equals 3.
Yeah, x-intercepts, right? So -4, 1, and 3. I'm also going to include the endpoints as well, since those are provided in our graph. Okay, above means positive slope, below means negative slope. So we start off below, so that translates to a negative slope. then above the x-axis, still above the x-axis, and then below the x-axis. So let's just have the arrows showing how my graph is, my actual G graph is moving. Now the arrows will tell us where do we expect a relative max.
X equals 3.
Yeah, not at 1, not at -4, because the arrows are not showing that relationship. So we know there's a relative max at x equals 3 because G prime changes from positive to negative. Okay, next up, find the absolute minimum value. Absolute min, absolute max, what does that remind you of? Which theorem is this?
Extreme.
Extreme value theorem. So extreme value theorem says test your endpoints and test your relative max, relative mins. So we're going to test the endpoints at -5, at 4, at -4, and 3. There's no need to test 1. I mean, you can test 1, but 1 is neither a relative max, relative min, so we can ignore it. So all we need to do is to test our 4 points, and whatever is our highest y value is your absolute max, whatever is your lowest is your absolute min. So technically, we can avoid testing G of 3 because why? Yeah, it's relative max. There's no chance relative max can be absolute min. So we can avoid testing 3. So we can just test -5, -4, and 4. So they're all will go back into this formula, right? Okay.
I can test all of them if I wanted.
Yes, you can. Yeah, you can. So let's start with -5. So -5 is from -3 to -5. So make sure that you always copy down exactly what the rule tells you. And if you want to make an adjustment, you can make the adjustment later, but don't do it until after you kind of see it with how they've defined it. So this one, I'm trying to read the graph, so I prefer going from smaller to larger. So I'm going to just flip the bounds so that it feels like I'm not trying to do opposites when I read my graph. So I'm going to flip the bounds, but if I flip the bounds, I got to push a negative in front. So let's look at the region between -5 and -3. Just a triangle below the x-axis, 1/2 base times height. I just get -1, right? Oops, sorry, -1 here and a +1 here. -5 to -3. So that's going to be 0. And so -0 is still going to be 0. So that's my order pair for G of -5. We're also going to test -4 because -4 is a relative minimum. That could be a candidate for absolute minimum. Again, follow what the rule tells you. The order does appear to be off, so I'm going to flip the bounds again so I can just not have to do opposites when I read my graph. Okay, what's the region from -4 to -3? A +1, so I'll put a +1 in this place, but then I'll keep track of the negative that I see in front of me. So -1.
Good morning. At the bell, all students will report to their advisement class. Advisement teachers should not releave their class until an announcement is made for the grade level. Please leave all belongings in advisement. Students do not leave advisement until an announcement is called.
Okay, we'll finish this on Monday, but essentially, after we find G of 4, we'll compare the y values. Your lowest is your absolute minimum. Okay. But we got through a good chunk. We'll have another day to review on Monday, and then you should feel good to be self-sufficient. We'll do review Tuesday or Wednesday, and then your test is Thursday. But in class, we'll have to start our next unit, but I'll have help sessions morning or afternoon if you need it. Okay, go eat your phones. Here. Okay, sure.
Which days?
John, can you get mine?
Yeah, 6.4.
John.
Or 6.5, sorry, 6.5.
6.5.
Okay, good. And then test reviews.
John.
You were to-
And then also page 1 off of the test review.
So I think I should.
You showed everything already. That's okay. If you show it to me, then that's all. Thanks.
Barely.
Okay.
You want Mike? You want?
I'm safe, like, I'm safe. Like, I didn't finish, like, I don't.
Oh, fun, this one.
I don't know if I showed.
That's like a, it's 29?
I think this is like last Friday's these problems. I pointed out. And then, okay, so problems. So. I think the first page of the, thing I have this. Other than that, I think that's everything.
Okay.
I'm gonna recover the last one on Monday. Five.
Okay. Sounds good.
Yeah.
I'll be here. Yeah. Okay.
I wonder how they got like the